All right. Let's start taking a look at this. What do we do to start? Yeah, when we have two logs that are being added together, there's not really much we can do. Unless we come through and we go, hey, wait a second. Addition is going to become what? Multiplication. So I can rewrite this as our log base 4 of our x times that x plus 6. Because our addition becomes multiplication. Equals 2. Then what we have is we have one singular log. So my left side is just one log, and it equals the number. So what can we do from here? You can distribute here. It doesn't really help all that much, but you can. I'll just say, let's do it since that was our idea. Log base 4. All that does is this makes this argument be x squared plus 6x. It's totally fine to do this here, and I know we've had that instinct a couple of times. It doesn't make any difference when we do that distribution. We need to put this in exponential form. So what we're going to do is we are going to grab our base power argument, and we're using that BPA is equivalent to log BAP, log base B of A equals P. That guy. To switch this back around, because we can rewrite this as our base of 4 to the power of 2 equals our x squared plus 6x argument that we had. Where can we go from here? If we had, I was gonna say, if we had a perfect square over here, we could do that. But this x, there's a wrench in that. So excellent idea, but it just doesn't work in this particular case.
Do 4 to the power of 2.
4 squared. 4 squared is going to give us that 16 equals x squared plus 6x. That came from this guy. What next?
You can do the X bar.
Yeah. Let's see if we can factor this thing. When we factor it, what do I need to do first?
Set it
Equal to 0. So we're going to have that 0 equals x squared plus 6x. The way we get it to equal 0 is we subtract 16 from both sides. So we have minus 16. Does this factor? Let's check. We want to see if we can find a pair of numbers that multiplies to our a times c, adds to our b. I don't like the way it's close together, but that's all right. Our a is the number in front of the x squared, so it's 1. Our c is the minus 16, so we have a negative 16 up here. Our b is the center value, so that's our positive 6. Is there a set of numbers that multiplies to make negative 16 and adds to make a positive 6?
8 and negative 2.
Mm-hmm. Yeah, if we take 8 times negative 2, we'll get negative 16, and 8 plus negative 2 gives us a positive 6. So filling in our x and box, or our box over here, we get our x squared from the equation, our minus 16 from the equation, and then these two pieces get this letter. So we'll have our 8x and our minus 2x. So what are we getting as our factors here? What happens when we pull these out?
X 8.
Mm-hmm.
X negative 2.
So we get x plus 8. And we're almost at the end on this one. X minus 2. What are our two possible solutions here? Because that's the whole point. We're trying to solve this. Get down to an x equals.
X equals negative 8 and x equals 2.
Mm-hmm. Because what we do is we set these two pieces equal to 0. So x plus 8 equals 0 gives us the possibility of x equals negative 8. And x minus 2 equals 0 gives us the possible answer of x equals positive 2. And then we have to check. If I substitute in negative 8 right here, is my argument still positive? No. So we know that this guy right here, oh my gosh, they made us do all that work and it doesn't even count. That is so extra. It is extraneous. If you just want to write like so extra, I totally would take it as well. I've had people do that before, but they just go so extra. But what it is extraneous. What about for our positive 2? Does that check or is that extraneous?
It checks.
The positive 2 checks. Because if I substitute in a positive 2 here, my base is positive and my argument's positive, so that one's good. If I substitute in a positive 2 here, my base is positive, my argument's positive. We're good to go. So this guy checks. So this one is our answer. We only have one solution on this guy. And it's this piece right here. Okay, so these solving ones you will see pop up, especially in Bulwark, because they're kind of complicated and kind of annoying, but really good practice for a lot of different things. Questions on this bit? All right. So we are going to be going on with new things. Dun, dun, dun. Everybody's favorite. So we're going to be in your notes packet. We are going to be on page 10. And it starts out with a couple of boxes at the top that you're not going to do. I don't like those ones. Doable, yes. Pleasant, really not. So we're going to be about halfway down the page where it says lesson 8-3 extra notes changes base formula. So page 10 in the packet, about halfway down the page. And once again, it starts out with asking us what's the common logarithm and what's the natural logarithm. What do we know about the common log? Talked about it several times. The base is 10. Common log, we will most often see written as just log of whatever the argument is. But this means the exact same thing. It is 100% equivalent if I wrote log base 10 of whatever that argument's. So it has a base 10. The natural log, what do we know about that guy? Is more often than not written as ln of whatever that argument is, but it is 100% equivalent to log base e of whatever that argument is. We are going to work with these guys a bunch today. We're also going to start figuring out how to use calculators for logs today. So, just say. So the ways we have to evaluate logarithms for this, how do you evaluate a logarithm question here? What we have so far that we can use is we can switch to exponential form. So option, I think you guys only one. We can today we're going to work with something called the change of base formula. So we could change the base to use a calculator. Or if we have logs on both sides, we can ignore the logs. That's pretty much the other way we have to do it. So today we're going to be working with our change of base formula. What this does is this is going to let us switch the bases so that we can use calculators to do things, because on the calculators, and this is true of about 95% of calculators, most of them don't have a way to do other bases. They have common log, they have natural log. Most calculators don't have more options than that. Most calculators just have those two guys. So we need a way to be able to evaluate anything. Log base 2, log base 7, log base 473, using either of those two pieces. So I'm good at talking. If we have a log with some base b and an argument, so we don't even have to have a power here. We don't have to have the whole statement. I could get this as a value, because I could rewrite this. Our change of base formula says this is the exact same thing as if I did common log of the argument over common log of the base. And I can put it as a fraction. Or we could do the natural log of the argument over the natural log of the base. So to be able to type these in the calculator, we put our argument over our base. They each get their own log. Since they are two separate logs in a fraction, I'm just putting this out there as something I see frequently. This is not a piece we can use our expanding rules on and put it as subtraction, because it's in two separate logs. It's not one log with division in the argument. So don't think of this as being an expanding or condensing thing. These guys are going to be what we're really focused with today. So we're going to start by looking at the bottom piece here and figuring out how this helps and what some of these values are. So those 6 pieces down at the bottom there. But this is one of those kind of really important formulas. So the bottom piece says evaluate and use the change of base formula if necessary. It's not always going to be necessary. The ways we can tell that this is going to be needed here is we have our base, we have our argument, and we're trying to figure out what the power is. So if I tried to switch this around into our exponential form, we would get base of 5 to what power equals 12. Do we know what power of 5 gets you to 12? Is that a thing we know?
I don't even think so.
I mean, it is, but it's not pleasant.
Yeah.
So what we're going to do is we're going to use our change of base formula here. We can choose either common log or natural log. It genuinely does not matter. I am going to use both, and I'm going to switch back and forth all day today because it genuinely does not matter. If you want to use one of them the whole time, that's totally fine. You should get the exact same answers as me. So what we're going to do is we are going to take, I'm going to start with common log. So we're going to do log of our argument, which is 12, over log of our base. It doesn't matter if we use common log or natural log as long as we pick the same thing for numerator and denominator. What this is going to give us is an estimate on this value. It's going to get us pretty gosh darn close. And the only reason it's not perfect is because calculators run out of space. So if we wanted to evaluate this, we could come into our calculators, use my very favorite button on these yellow calculators, which my touch screen is also not working, so I can't do it with the buttons. Second column, third button down, we get the fraction. In our numerator, we're going to put our common log of 12. Boop. Hit the down arrow, and we can do our common log 5. Boop. We should get about 1.543959311, blah, 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 blah. We're going to take this to, let's go with 2 decimal places, just because it'll get us close enough. So 1.5 1.4 would be our estimate here. It's about 1.54. And if you want to test that, you can come in here and say, all right, but is that actually kind of close? If we did 5 to the power of 1.54, gets us pretty gosh darn close to 12. If I could type in this whole thing right here, it would put it right at 12. So it's finding the power of decimal grossness that gets it to the value that we want it to be. So a lot of times these are going to give us estimates. It's going to get us close. So let's try that again on number 2. Again, I like for us to think about if we even need to use change of base formula. So on this one, our base is 7. We want to know that power. Do we know what power of 7 gets it to be 18? No. So since we do not know what power of 7 gets us to 18, we are going to use our change of base formula because we want to know what this equals. So again, I'm going to switch this time and I'm going to use natural log. It's not any different. We're still going to do our log of our argument, 18, over the log of our base, which is 7. And again, it genuinely does not matter if you use natural log or common log, as long as you use the same top and bottom. So in this case, I did natural log of 18 over natural log of 7. And we get 1.485357, blah, 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 blah. These will be long. They will be very, very decimally. We're going to just take a couple of decimal places and go from there. So we've got 1.4, that's a 5, so it rounds that up, 1.49. So if I raised 7 to the power of 1.49, we would get right about 18. And just to show you, you do not have to do it both ways, but just to show you, it really does not matter if you use common log or natural log. If I did the exact same thing, but with the common log instead, we get the exact same answer. So it genuinely does not matter which one you use. Let me use the big screen to show that. It does not matter if you use common log or natural log, as long as you're matchy-matchy. Has to be matchy-matchy. Okay, questions on these first couple? Let's keep going. We're going to practice these a few times before we look at the solving stuff that uses these. So number 3. Again, I want us to check and see if we even need to use change of base here. So our base is 2. We don't know our power. That's what we're trying to find. We want to know when that equals 16. Is that something we know? What will our power be then? 4. So on this one, we don't need to use change of base. We can. It totally works. If I do, this is not something you need to see, I'm just going to show you. If we do log of 16 divided by log of 2, it spits it out. It tells us it still works. We just don't necessarily need to use it because we know 2 to the 4th is 16. So it's doing the things that we can do with our brains. It's already in a log. So number 4, how could we evaluate that? I was going to say, it's base 10. So you can do it with log of 15 over log of 10. But also, this straight up is the common log. So if we need a decimal of this, we can just go log of 15. Boop. It is 100% the exact same thing we get if we're going to do log of 15 over log of 10. Exact same decimals. Again, same exact thing as if we did ln of 15 over ln of 10. You're confused why I'm doing that the very hard way, but that's okay. We get the exact same decimals either way. So it doesn't matter how we do it, but since this is the common log already, the easy way is just to type that sucker in. Because this is just about equal to, I even forget already.
1.76, so that would be 1.18.
Yeah, 1.18, 1.18. 1.18. So how would we set up number 5? Log of 11 over log of 3. Because I do not know what power of 3 would get to 11. So if we do log of 11 over log of 3, what are we going to get? What's our decimal version of that?
2.18.
Yep, 2.18, 2.18, something like that. What about for number 6? How would we set this one up? Yep, you can do log of 20 over log of 8. I was going to say you could also do ln of 20 over ln of 8. It genuinely doesn't matter. I just am writing both on here so that we don't get stuck in that has to be common log kind of mindset. Either way, you're going to get 100% the exact same answer. What do we get as our answer on this guy? 1.44. Okay, so now we have a tool that'll let us change our base as we're going through things and trying to solve them. The reason this is helpful is because a lot of times when we're dealing with exponential pieces, we're not actually given common logs or natural logs, but we want real answers. Like I want to know what the number is. Log base 3 of 11 is all well and good, but I don't know how far that is. If I'm saying I need to go log base 3 of 11 miles, but 2.18, I can do that. I can do that. Log base 3 of 11, I not a clue if I'm going a half a mile or 20. So when we're going to use these is when we have problems like on the very next page on 11, we're just going to do a little bit. Sometimes our solving stuff isn't going to look like logs. It's going to look like exponentials. So the tricky point on this guy is that our variable is up here in the exponent. We have an x in the exponent. So what we're going to need to do to be able to solve things that have variables in the exponent is we need to get that power out of a power and down into like the regular line of numbers. And the way we do that is that's when we're using our BPA that is 100% equivalent to our log base B of A equals P. So we're using our BPA log BAP again. Shock. I know. But in order for us to be able to switch things from our exponential form to get our power by itself, I need to have just the one piece over here. So what can I do in order to get my guy that's got the variable, this guy, all by himself? Somebody playing bubble shooters? Like I was hearing the blah, 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 like the ads. Turn your sounds off, y'all. Especially if you're not paying attention.
Subtract 5.
Yeah. We need this guy by himself. So I gotta get that 5 to go away. So let's subtract 5 from both sides. Minus 5, minus 5. That's gonna give me 10 to the minus 4x equals 32 minus 5, 27. I was gonna say, we've got calculators, but I know we're also writing, and so it's also early. I'll give us that one. I want to get my letter out of this freaking power because it's in the way and super annoying. So now I've got this exponential statement. Let's switch it into log form. So what's our base on here? 10. So we have log base 10. I am going to write it out, but it is the common log. Yes. I was moving it up a line. There we go. Log base 10 of our argument 27 is going to equal that power of negative 4x. Which again, we just noticed that's our common log. That's a thing we can do stuff with. We've got the common log, because base 10 is the common log of 27, which is just a number, a gross number, but a number, equals negative 4x, because this is the common log. I'm going to write that down here just so we have it.
So when it's the common log, when it's 10, then you can just put it as log 27.
If it was base E, we could just write it as ln. You don't have to write this step, but I like to, especially when we're very new at it, to remember what the heck happened here instead of just going, magic happened and things moved.
So if it was like log 2 or something,
Mhm.
you would keep the 2. You would.
Correct. So this is a number. It's a super gross number. It's kind of like having a pi or an E here. It's gross. I'm going to leave it for now. But I still want to get my x by itself. So what do I need to do to that side to get my x by itself?
Divide negative 4.
Divide both sides by negative 4, because I want to get that x by itself. So if I divide this side by negative 4 and this side by negative 4, that's going to tell me that my x equals this super gross fraction. Log of 27 over negative 4. This is what we call our exact answer, because this is the correctest it can be. Again, if I'm trying to go that far, I don't know what that is as an actual distance or unit of time or whatever we're looking at here. I don't know if that is 27 seconds or 5 hours or 12 years. I have no idea numerically what that is. So the way we do that and the way we get our decimal estimate is we're going to type that sucker in the calculator. So to find our actual value that's actually, real life usable on stuff, we're going to put together a fraction. And in this case, we have our log of 27. That is not what that is. I hit the wrong button. There we go. Log of 27 over negative 4. It's because my buttons are very tiny when I have it on the screen. And my touch screen's being a jerk because my computer's being a jerk. So we get negative 0.3, we're going to round it to 2 decimal places, 6, because the 7 pushes our 5 up. So our decimal approximation is that x is just about equal to negative 0.36. This is our exact answer. This is our decimal approximation. So now that we have the tools where we can start putting things into the calculator and getting decimals, we're going to start to do so. Sometimes it's going to be stuff like this where we wind up with a common log right off the bat. Sometimes we're going to need to use our change of base formula. Oh, I wonder what happens with numbers. We're going to do number 2, and that'll be the last one for today. So questions on this one before I leave the page?
Are we ignoring the signs? Like the plus, multiplied, that negative, that stuff?
No, leave it there.
Okay.
Just like we did on this one, we had our -4 that, I was an eraser, not a laser pointer. Our -4 that came down here. We're keeping all these signs. We subtracted 5 because it was a positive here. So the signs are still important. We put in our -4 over here. It's, it was our negative.
I meant like how it says 5 plus 10 to the power of.
If it was just 5 plus 10, that would be different. This 5 is not being raised to the to the power of. This 5 is separate. That's why we subtracted it first. So we need the piece that has the exponent by itself first, because order of operations wise, we would need to do our exponents before we could do any multiplying. So in order to mess things around, I got to get the multiplying out of the way so I can look at my exponent by itself. So, oh, we didn't even look to check here. It's like, if you want to check this, you could type it in here and it would get us really, really close. But most importantly, what we need to make sure is that on our logs, none of our bases are negative. None of our arguments are negative. We didn't have any variables in either of those pieces, so that's going to be totally fine. Our variables are only in the power. So if we look at number 2, it's very, very similar. So on this one, I want to get my piece that has the exponent by itself first. So we're going to take this guy, and I want to get him by itself. That's the piece where my variable is. I'm trying to figure out, in this case, what V is. That is a V. I know it looks kind of U-ish, but it is a V. Math fonts are weird. Ooh, careful. What's happening between the 2 and the 18?
Multiplying.
Multiplying. So how do I get rid of it?
Divide.
Divide. We need to divide both sides by the 2 to get this guy to leave. So we're getting it by itself because I can't bring that in because powers happen first in order of operations. So we got to be real, real careful. So we have our 18 to the power of minus 5v equals 62 divided by 2,
31.
31. There are a couple of pathways through this one. I'm going to show you the one that uses our changer base like we've already done. Yes, dear.
Why do we divide the 2 instead of subtracting it?
Because it's being multiplied here, 2 times 18, as opposed to on this guy it was 5 plus. So here we subtracted to cancel out that plus part. And on this guy, since they're being multiplied, we've got to divide it away. So it's just like if this was saying 2x equals 62, we would divide by both sides by 2 to get the x by itself. In this case, we're just dividing dividing both sides to get the 18 to the minus 5v by itself. Because once we get it here, we can use our log property to be able to switch this around into log form, which is going to give us our log base 18 of our argument 31 equals minus 5v. I should have had that bit be in purple. Just change the color real quick. Because these aren't going to let me do it. This was our power. So again, what would I do to get my v by itself? The left side's gonna be a mess, but I want to get v by itself.
Divide by -5.
Divide by -5. So if I divide both sides by -5, that's gonna get the v by itself here. So we're going to have that v equals our log base 18 of 31 over -5, which is absolutely fine and technically correct. I don't have any idea how far that is, what time that is, whatever unit we're looking at here, not a clue what that is. So if we want to get our decimal approximation, we're going to need to use our change of base formula here. Sorry, my pop socket's like cap just popped off and was feeling weird. So to get our decimal approximation on this, we need to use that change of base. So our numerator up here, you can either do common log or we can do natural log. I'm going to do natural log just because we've used common log a lot here. So I'm going to do ln of my argument 31 over ln of 18. And if it helps, you can do that as your numerator like this and do it as a fraction in a fraction. It's super gross to look like that, but it is totally fine. Or we can go that, hey, this is ln of 31 divided by ln of 18 and also being divided by -5. So you could write this, and this will be the easy way to write it, as our ln of 31 over -5 ln of 18. It means the exact same thing. It's just that they're both dividing that 31. We can combine those two denominators together. Do not have to. You can type it in the calculator absolutely either way. And I will show you how to do both for our decimal approximation. So we can either do our fraction, where we have in our numerator another fraction that we've got our ln of 31 over our ln of 18 over -5. You can set it up as a fraction in a fraction. It works. It'll do it. We can also do our ln of 31 over our -5 ln of 18. They both are going to give us the exact same answer. Exact same. So it does not matter how we write it. It's still going to give us that decimal approximation of -0.24. We weren't getting recorded announcements today. Whatevs. Okay, so we're going to work more with this solving stuff tomorrow, and we're going to keep working with our change of base and how we do this solving stuff more, because they feel kind of weird and they're kind of gross. But we're going to use these getting us through the rest of this. So,
okay, more homework.
But I think a nice picture is actually the last one in the chapter. So this includes all of our solving stuff we did today using our change of base. It includes some of our condensing stuff. There is a technical issue on this one.
Yeah.
Okay, I'm gonna pass them out tomorrow because we have one that has dog. And it's super gross. So I'm not gonna pass it out to you today. Because there is a, like,
Oh, I see.
blah, blah. Blah, blah.
How does that even work?
That's called, one of us likes to use Google Docs, one of us likes to use Word, and they like to argue. Google Docs and Word do not play nice together. So I will get those reprinted here today, and I'll pass those out tomorrow. So they're not due until Friday at the earliest anyway. Honestly, probably I'll have it be Monday, so that we have the whole week and the whole time to work on them. But we'll deal with that. But yeah, no, there's a technical problem on there. So I'll pass those out tomorrow. So huzzah. No homework today. We love that. Let me see if we're getting actual announcements today. I didn't think we were. Oh, we might be.